Hello, everyone. My name is Hanrui Wang. I'm a PhD student at MIT working on content architecture and efficient machine learning. I'm very glad to introduce our work on SpAtten, efficient sparse attention architecture with Cascade token and head pruning. As we know, NLP techniques have been widely used in many real-world applications, ranging from chatbots to machine translation. Their impressive performance comes at the cost of low efficiency as the model size and computation are both increasing exponentially. Therefore, specialized NLP algorithm and hardware co-design is critical to solve this challenge. In recent state-of-the-art NLP models, attention is the most important layer because it extracts relationship between tokens. Here we profile the GP2 latency on different CPUs and GPUs. We find that attention takes over 50% of the overall latency, although its computation only accounts for less than 10%. Inside attention, the matrix multiplication only takes 27% latency. Other memory operations such as hash split, transpose, and concatenations take over 70% of latency, which make attention very inefficient. Therefore, in order to accelerate attention, we propose SpAtten, an algorithm hardware co-design for attention layer computations. We leverage pruning and quantization opportunities to reduce computation and memory access, and design specialized hardware to accelerate the complex data movements. The first approach is cascade token and head pruning. The intuition is that human language have high redundancy, so it is desirable to find useless information and remove their computations. Here we show an example. The task is to classify whether this film review is positive or negative. The input to the first BERT layer contains all 11 tokens and 8 heads. The heads here can be considered as multiple parallel branches for computations. Different branches have different functionalities. After the first layer, we identify unimportant tokens and heads and remove them. In this example, we remove tokens like the, almost, which does not have significant contributions to the overall meaning of the sentence. Therefore, the second layer only needs to process a shorter sentence with fewer heads. Similarly, more non-essential heads and tokens are removed, and the last layer only has 2 tokens and 4 heads. If I only show these 2 words, film perfect to you, are you able to determine whether it is positive or not? I believe it's obvious. Viewed from a higher level, the attention computation has inputs, query, key, and value matrices. The feature embedding are chunked to multiple heads, such as 8 heads in this example. QKV inputs of layer 1 go through attention layer, FFN layer, and QKV FC, and get QKV inputs for layer 2. Layer 2 outputs further generate the QKV of layer 3. During this process, the number of token heads are the same. However, not all tokens and heads are created equal. There are opportunities to find unimportant token and heads in the front layer and remove them in later layers. In order to do this, we need to use an indicator called importance score to tell us which token and heads are unimportant and prune them away like this. This corresponds to removing tokens and heads in the previous example. Similarly, for the remaining token and heads, we can again evaluate their importance after layer 2 and prune unimportant ones, which correspond to the remaining 2 tokens and 4 heads in the example sentence. During this process, the pruned token and heads will never be used in all following layers, thus it is called cascade. It helps us to reduce the computation and memory access because we only need to fetch and process remaining tokens and heads. In order to support the pruning, we design a top-K engine to select top several important tokens and heads and remove others. The top-K engine has a quick select module to select the K's largest element. The quick select has 16 smaller comparators and 16 larger comparators, so it can generate outputs in high parallelism. We also propose progressive quantization. The core idea is to reduce DRAM access for memory-bounded generative NLP models such as GP2 and GP3. We achieve this by eagerly fetching MSBs and lazily fetching LSBs. Intuitively, for simple sentences, we can just use MSB to understand sentence meaning, but for difficult sentences, we need more information. Here is an analogy. For this sentence, the 4 information is in the DRAM. We only fetch part of the information to the on-chip buffer. If the confidence about the sentence is high, then we do not need to fetch LSBs. Otherwise, for this example sentence, if the confidence is low, meaning the information is not enough to get meaningful results, then we need to fetch LSBs. We also designed an accelerator containing specialized modules to support token head pruning and progressive quantization as shown here. The critical path here is fully pipelined to increase the throughput. We implemented and synthesized architecture with TSMC 40nm technology. SpAtten has 18.7 millimeter square area and 8.3 watts power. It consists of 1,024 multipliers, 392 kilobytes SRAM, and 16 channels HBM. Each provides 32 gigabytes per second bandwidth. The performance on summarization stage is 1.6 teraflops per second and 0.43 teraflops per second for generation stage. We compare the latency and energy with general-purpose CPUs and GPUs. Over server-level CPUs and GPUs, we can have 100 to 300 speedup and over 1,000 better energy efficiency. Over edge devices such as Nano GPU and Raspberry Pi, we have more than 1,000 speedup and up to 1.9 thousand energy savings. We also compare SpAtten with state-of-the-art attention accelerators. A3 is an ASIC design with support for local key and value pruning. We have 1.6x speedup and 1.4x energy savings. MNFuzz is an FPGA design with local value pruning support, and we have around 3x speedup and energy savings. As conclusion, we propose SpAtten Accelerator to push the frontier of green AI and tiny AI. SpAtten accelerates NLP by removing redundancy in human languages with Cascade token and head pruning, local value pruning, and progressive quantization. It is also equipped with a high parallelism Topk engine and specialized data paths and operators to improve the efficiency. For more information, please check our website at spatten.mit.edu. Finally, as take-home, SpAtten removes redundant tokens and heads and saves computations and memory access of NLP models. Thanks for listening.